See, the geometric definition, the dot product relates the vectors a and b to the angle theta between them. A dot b, that is a dot product b, equals absolute a times absolute b, the unit vector a times unit vector b times cos theta. So if you divide a dot product a dot product b divided by the unit vector a times the unit vector b, then you get a cos theta. And if you get cos theta, right, then you can find out the angle between them. So that's basically like this: a dot b divided by absolute a times absolute b. This equals cos theta. Okay. So this is obviously useful to understand that a dot product b or dot products somehow can involve the angle between them, between the two vectors. The two vectors that are being dot product, you can have the angle if you divide it by the unit vectors. What does that mean in reality? Well, if we draw an XY graph, if we have a flagpole here, and we're measuring theta here, right? We know theta is, this is opposite, this is adjacent over hypotenuse. Adjacent over hypotenuse, right, is, let's say this is A, this is B, hypotenuse is C, all right? We know what C is, we know the length of C, we know the length of A, we do A dot C, this equals cos theta, because adjacent over hypotenuse equals cosine theta. Cosine theta is adjacent over the hypotenuse. We know A because this is the x-axis and this is the y-axis. We know C because that's the length of our vector. So we know the length of a vector B, or C in this case, the length of vector C, and we know the length of vector A, how far it drops down. So how do we know the length of A? What is the length of A? If you have a sun here, and this is figuratively speaking, at the top of Y, shining down rays, then the flagpole will cast a shadow up to A, the length of A, right? So it's casting a shadow. The flagpole casts a shadow. So what you're trying to find out is, right, how much of a shadow does it cast? That's okay. So for example, if it's perpendicular, right? If the flagpole is perpendicular, it won't cast any shadow, so it would be 0, and therefore it would be cos 90, which is 1. No, what's cos 90? Cos 90 is 0. So basically it's saying the shadow casted by this straight up flagpole is 0 distance, 0, because it's perpendicular. So if it's 0, it has no reliance. Okay, but a flagpole that is fully flat on the ground here, right? Cos theta will be the angle will be 0 degrees. Cos 0 equals 1. Cos 0 degrees is 1. So that's one you can think of as 100%. So the flagpole will cast 100% of its length as a shadow onto the x-axis. Okay, so what does that mean? The shadow represents how much it depends on the flagpole's length. So the flagpole's length determines how much that is dependent. So, so you can think of it either way, one way or the other. The sum of xi times the weighted weight ij here. You can think of the weight ij as the flagpole and xi as the x-axis, and how much the flagpole has a bearing on the x-axis is how much they get the sum of the multiplication, the dot product. So the dot product of the weights on the x-axis and the x variable determines the shadow. The shadow is everything. So you can imagine this flagpole being Wij and here being Xi. So if they get multiplied together and summed, you get the shadow. All right, so now you know, if we go back to the earlier whiteboard, in here, Yj equals the dot product of xi times Wij. So Yj is the shadow that is casted by W and Xi. Why is that important? Well, it shows how much the hidden variables, hidden values, hidden nodes get affected by the weights and the input nodes. So if the input nodes has a certain structure, and the weights are chosen by how you choose a weight. Well, that's a funny thing because you don't know what weights would be good, but you know you give a particular output, true or false, or boy or girl. You know that this image is a girl, and the inputs give it the pixels of the girl, and you don't know what the hidden values are. You randomize them initially, and the output is supposed to be true or false. Now, what you do is you also randomize the weights. What you do is you tweak the weights so that they get a hidden value such that it gives the output of a girl. Result is a girl. So you're trying to find out a particular set of weights such that the hidden values always get a girl. That's training. That's what happens when you train an artificial neural network. So when when you're during a train of an artificial neural network, you adjust the weights and biases, not the hidden values. The hidden value activations are simply an intermediate outputs taken by the network during the forward pass. So that's basically what happens. The hidden values get calculated by the weights multiplied by the input values. Another thing that's also important is the fact that you might get something called a Fourier transform, and that's also xi times exp exponent minus imaginary jwt xt. So this is a Fourier transform, okay? And again, it's the same form. It's a sum of two products being multiplied together. Xt, x vector, times exponential whatever jwt. J is for complex number in engineering. Omega t is the frequency. So basically it's saying if you multiply the frequency and the input vectors of your analog signal, your xt, you get a Fourier transform. What does that mean? It means, going back to the flagpole example, it means this is your frequency, this is your input, and the shadow that gets casted is how much your input depends on that particular frequency. So actually the graph may look more like this. This is x, and this is your frequency here. Either way, it doesn't really matter because it's just a method of perception. You can readjust the phase, not just the phase, but you can adjust this x-axis and y-axis accordingly. You can switch them around, and you just adjust the f and x. The theta will still be the same. It'll still be adjacent versus over hypotenuse, and so that's why it's a dot product, right? So it's a shadow. It's how they shadow each other, right? And so that's a Fourier transform. It's saying how much does this waveform x, the x vector, how much does this waveform depend on a particular frequency? And so you get a frequency graph, a frequency domain graph, and you see all the frequency domains, frequency domain graph over FFT. So let's see, this is a waveform in time, and this is a frequency. So basically, these are what you would call transforms, right? So this is these neural networks are doing a transform of some kind, right? So you'll have different types of transforms. So different types of mathematical transforms. Neural